Um, there are couple of major components in operating system. One is the processes, you know how the particularly the scheduling uh, algorithm, the scheduler. So this is a major one of the major parts in the operating system that manage the processes in a multi-programming environment. Now, another big part of the operating system is the memory management, because memory is so important that there are multiple when processes are executing in the shared environment, then each process need to take some resources like CPU time and also memory space. So then the operating system need to make sure that each process get a fair share of the memory space, and also operating system should be able to track, which part of memory uh, belongs to which particular processes. So memory management is another very important part. Uh, the third part is it's called a file system. Uh, Basically, it's the management for the hard disk space, the storage space. Okay. Now, so let's actually finish up the deadlock. Now, deadlock actually happens when multiple processes, multiple process, they're running P1, P2, P3, running in the system, and these process need to, you know, need, may request some hard drive, memory, or we call these resources. Okay, so you have various different resources: resource one, resource two, resource three, resource four. Resource one could be a storage, resource two could be memory, and the resource three could be a printer. Resource four could be a scanner or other um, devices. So during the execution of a process may request to use the resources at a different time. So now the resources are shared. Okay, resources are shared just like a memory. So they're shared. So it's not actually dedicated to a particular process. They may be shared by many different processes. So that's going to actually cause some kind of situation that you know while the resources are shared, so they are limited. So when process one requests for a resource, it may or may not be available. So in that case, the process one may not be able to continue to execute until process one gets the resources it, it, it requested. And then the process one can continue. Okay. So now in that scenario, so if process two also requested for some resources to continue to execute, then these process may actually each process may have grabbed some of the resources, but is still waiting for some more resources to continue. And another process also is grabbing some of the resources and still waiting for more resources to continue. And then there might be some kind of situation that the process one may grab some resources and request for some resources that the process two is grabbing, is currently holding. And process two is requesting for resources that the current process one is holding. But each actually requires these additional resources to continue the execution. Now, in this case, both process one and process two cannot continue because process one hasn't got the resources it required, it requested. But these resources are held by process two. And the same vice versa. Process two is actually requesting for some resources, but these resources are currently held by process one. So each one are holding the resources that the other process is requesting. That situation is called deadlock. Okay. Now, in the operating system design, people try to, create some kind of scenario that so they use the resource allocation graph to create this, scenario. So and then they try to find a solution. How can we avoid any kind of potential deadlock? Okay. Now, a process may actually grab some resources and waiting for some other resources. And in this case, the process one has to be waiting. Okay, waiting the other resource to be actually freed, and then the process one can take them. So they need to wait, and then so the waiting time could be long, could be short, and could be forever, like a deadlock situation. So that's why they want to use the resource allocation graph to at least shows the current allocation of resources to processes and the current request by the process for the new resources. And so this graph gave you some kind of overall picture of which processes are holding which resources, are requesting for which resources. So this is a resource allocation graph. And based on the resource allocation graph, you can probably figure out, whether there's a deadlock. Okay. If there's no deadlock, that's good. If there's a deadlock, how can I resolve it? Or if you ask the further, then you may actually think about, before you get into the deadlock situation, can I avoid this deadlock situation? Okay. That's something we try to talk about. So now the resource allocation graph basically use a couple of symbols. And basically we use circle to represent the processes and a rectangle to represent resources. And for each rectangle, there's a small circle inside the rectangle. Each small circle represent an instance of of the resources. That means it's a one copy of the resources. Now, if you have three circles inside, like this case, that means this particular resource has three instances or three units. Like the case for the printer, you may have three printers connected to this system. So now three processes can simultaneously use the printer because each process can grab a printer. Okay. Now in the resource allocation graph, we also use the edges. Okay, edges is just like a line with the arrow. Okay. So there are two actual directions. One is the arrow actually pointed to an arrow points to a process from resource. So that means this is actually the allocation. So that means this process is currently holding this resource. Okay. Now the other one, the arrow is pointing to the same direction, but you find out the process is actually on the left side and resources on the right side. So that means this process is requesting for this resource. Okay, is requesting. So this is requesting, and this is allocation. Okay. Now the requestion, a request, the the request may quickly turn into allocation if process is requesting a resource and the resource is available, and then the arrow may switch direction quickly. The requesting is becoming the allocation. But if a process requests for resources and the resource is not available, then the request stays as a request. Okay, so that's basically what the resource allocation graph is supposed to actually show you. So now here's an example of the resource allocation graph. So you have three processes, P1, P2, P3. And you have two resources, R1, R2. So R1 has 4 instances or 4 units. R2 has 4 units. And so then initially P1 is currently holding the resource 1, holding 1 unit of the resource 1. And the P2 is also holding 1 resource, a unit of the resource 1. Now, there's actually three units for resource 1. Okay. Now, R2, P3 is currently holding 2 units for the resource R2. And the P1 is holding 1 resources for the for the resource R2. And there's a one free actually unit for R2. Now, suddenly, P3 and P2 request for, remember, the arrow, the edge actually from the process to the resource, that's request, right? So this is request. Okay. P2 make 2 requests to the resource 2. Okay. And the P3 makes 1 request to the resource 1. Okay. Now sounds like this is kind of a situation, but you realize that P1 is not in the deadlock situation, right? P1 is not blocked because P1 is currently holding resource 1 unit of resource 1, and the P1 is holding 1 unit of resource 2, and the P1 has no request, right? P1 actually holding 2 resources, but there's no request, so there's no arrow point out from P1 to anyone. So there's no such a request. So that means P1 actually is currently getting all the resources it needs. So P1 should be able to continue to execute. And once P1 complete the execution, P1 can release the resources. So P1 is in good shape. There's no actually, P1 is not blocked. Now, what about P3 or P2? P2 is currently holding 1 unit of resource 1, but is requesting for 2 units of resource 2. What do you think? Do you think a P1 can get all the resources and continue?
You're asking if P2 can continue?
Yeah.
No, it can't because there's only 1 unit of R2 available, and it's requesting for 2.
Yeah. P2 is requesting for 2 units of R2, but there's only 1 unit of R2 is available. So P2 has to wait. P2 is blocked. Hopefully, P2 is not going to be blocked for long. Why? Because P1 gets all the resources it needs, and the P1 can hopefully sooner or later P1 going to be complete its job and then release one of the resource 1 and then one of the resource 2. So then once P2 finish the job, P2 may release one of the unit. So then P2 can get these 2 units. But at this moment, P2 is blocked, right? P2 is blocked. What about P3? P3 actually is currently holding 2 resource 2, 2 actually R2, and P3 is requesting for R1.
P3 can continue because it's requesting a unit of resource 1, and there's like 2 units available, and it only needs 1.
Okay, so that request can be actually achieved. So quickly, you can change the arrow, direction of the arrow, right? So the request becomes holding. Okay, so quickly, the request becomes actually, you know, will be achieved. So in this case, so P3 is not blocked, even though P3 is requesting, but P3 is requesting for resources which is available. So P3 is not blocked. So in this case, P3 has an outstanding request for 1 unit, but since unit 1s are still available, P3 is not blocked. So P3 can continue. So only P2 is blocked. And hopefully, P2 will not be blocked for long because P1 can finish. Okay. Or P3 can finish and release both of these resources. So in this case, two processes are not blocked. One process is blocked, but there's no deadlock, right? Deadlock is kind of like a circular waiting. Okay. Now here we take a look at another example. Okay. Um, so again, so as I said, as we say that a reusable resource contains one or more identical units, each of which may be requested and used by a process on a non-shared basis. Okay. Now, just realize that deadlock involves at least 2 processes and 2 resources. So in that case, now the simplest deadlock case is like this. So you have process 1 and process 2, and resource 1 and resource 2. So process 1 is currently holding the resource 1, and the process 1 request for resource 2. Okay. And the process 2 is currently holding resource 2, and the process 2 request for resource 1. And I assume, oh, I'm sorry, I use rectangle. And I assume that the both resource has only 1 unit. Okay, only 1 unit. That's the simplest deadlock case. Because process 1 cannot continue because process 1 request for need to get the resource 2 to continue. But process 1 is holding resource 1. And the process 2 cannot continue because process 2 holding resource 2 but still request for resource 1. Now, that's the deadlock situation. If process 1 never gave up resource 1 and process 2 never gave up resource 2, and both processes going to be in the situation that they both cannot continue. So that's a deadlock. So that's the simplest deadlock case that involves 2 resources, 2 processes. Is there any questions? Now, the diagram below basically shows the deadlock situation, which involves 3 processes and 3 resources. Now we assume that in all the resources have only 1 unit. Okay, each resource has only 1 unit. Now in this case, process 1 is holding R1, process 2 is holding R2, process 3 is holding R3. Okay, now process 2 is requesting for R1, process 3 requesting R2, process 1 requests for R3. That's another kind of situation of deadlock. Okay. Oh, I'm sorry. Process 1 actually request for R1 and process 2 request for R1. But process 1 actually get the R1. Okay. And the process 2, the request from process 2 has to, continue with the request because there's only one unit. And then both process 2 and the process 3 request for R2, and the process 2 get the resource. And the same thing with this case. Process 3 and the process 1 both request for R3, and the process 3 get the resource, and the process 1 has to wait. Now, that's the worst scenario. Okay. This is just like the dining philosopher problem, right? So you just actually grab one and waiting for the other one, and the other one is grab one and waiting for the other one, and grab one and waiting for the other one. And unfortunately, it's just actually form a some kind of loop. Okay. Now that's a deadlock situation. Now, how can you identify the deadlock situation? Okay. Now, suppose that each resource has only one unit. Now, you can actually easily figure out there's a deadlock or not. The deadlock must have some kind of a loop. Okay. Deadlock involves some kind of a loop. Okay. It's a closed loop. Let's take a look, in this case. So in this case, so the loop actually starts from, let's say here, from P1. So P1 request for R3, and then R3 is currently in the hand of P3. And the P3 cannot continue, is requesting for R2, but R2 is in the hand of P2. And the P2 cannot continue because P2 is request for R1, and R1 is in the hand of P1. So basically, you are actually going into center kind of a closed loop, right? Going this way. Okay, it's a closed loop. So in this case, unless one of the process give up its resource, and this gonna break the loop, then it's gonna work. Okay. Now there are two actually other scenarios that eventually gonna avoid the deadlock. Okay, with the same kind of situation. Suppose that the P1 and P2 are fighting for R1, and the P1 and the P3 fighting for R3, and the P2 and the P3 fighting for R2. Okay. Now, if it's not like the situation that the P1 gets R1, P2 gets R2, P3 gets R3, and that's caused the problem. But if we slightly switch it, okay, so let's say P1 and P2 both request for R1, okay, and the P1 wins. So P1 get the R1, and the P2 has to wait. Okay, and then P1 and the P3 fight for R3. Okay. Now, instead of letting P3 wins, we let P1 wins. Okay. So in that case, unfortunately, P3 has to wait, right? P1, P2 has to wait, but P1 gets whatever it requested, and the P1 can continue, even though there's actually waiting situations. P2 and the P3 are blocked, but the P1 is not blocked. Unlike the previous case, then when P1 and the P3 fight for P1 and the P3 fight for R3, and the R3 actually P3 gets the resource, and the P1 has to wait. So that means P1 is grabbing something, holding some resource and waiting for the other resource. That forced the P1 to be blocked. Now, in this case, if the fighting actually the result is different, and the P1 actually gets R3, so P1 can actually get both of the resources, and then P1 can continue the execution. And it doesn't matter how long the P1 going to actually execute. Eventually, P1 going to be able to finish the job and then release both R1 and R3. So then P2 and P3 can continue. So in that case, there's a waiting situation, but not no deadlock situation. Or if in that case, okay, so if P1 and the P2, P3 fighting for R3, and P3 win the fighting and get the R3, so P1 has to wait. Okay. However, the fighting between P2 and P3, and the P3 actually eventually gets R2. So P3 gets all the resources and it can finish. So P3 can eventually release R2 and R3. Once P3 release R3, and the P1 can get R3 and continue to do the job. Okay. So in any other situation, deadlock never gonna happen. The only situation when deadlock happens is it's just fall into some kind of circular wait. Okay, remember the case of dining philosopher, right? The dining philosopher, we have 5 philosophers and 5 forks. And then the most the 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 best the worst scenario is P1, the one philosophy grab the left one, looking for the right one, but the right one is held by the other process, other philosopher, and the request for the right one for this process, for this philosopher, and this is held by this one, and the request for the other one. Oh, I'm sorry, held. Oh, I'm sorry, I just messed up. Let me actually redraw this. Okay, I have to be careful between request and allocation. Okay. So let's see. Okay. Now I should change the color for the. So this guy, this philosopher, grab, currently holding this fork and requesting for this fork. And this guy holding the fork and request for the right fork. And this guy holding the left fork and request for the right fork. And this guy holding the left fork and request for the right fork. This guy holding the left one, request for the right one. So you see that each philosopher is holding one fork and request for the other fork. And it's the same kind of situation for all philosophers. Now we are in this closed loop, right? So you have an arrow point here, continue, 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 continue. So we are actually fall into something called a circular wait. Okay. That's the worst scenario, just like this case. It's a circular wait. Okay. So this is actually to break the deadlock, you need to actually avoid the circular wait. Okay. I think that's pretty much all I want to talk about for the deadlock. Now, if you actually read the Zai book, the Zai book give you a little more, cases for the deadlock. But I decide I'm not gonna try to cover all the actual deadlock situation. So just give you some kind of concept. What does deadlock means? Now, in reality, for most of the operating system, so they don't actually provide any mechanism to prevent a deadlock for various different reasons. Number one, deadlock may happen, but the chance for deadlock to happen is not really that frequent. Okay, so then we may choose to ignore the deadlock. Okay, now the other thing is, even though the deadlock happens, to provide the solutions to prevent a deadlock, in order to prevent a deadlock, you have to do a lot of things. You have to actually create a lot of code, like a deadlock prevention piece to prevent a deadlock. And these gonna actually take some resources. So to prevent a deadlock, you have to sacrifice some of the performance for the operating system. Because to prevent a deadlock, for each process, when each process requests for something, and then you need to check the situation. Are we in the deadlock situation? No? Okay, let's continue. And then every time when things happen, when a process requests for resources, when a process release the resources, then you have to check these, deadlock. You have to check this, something called a resource allocation graph. So you have to check the graph each time when situation changes. So that itself is very costly. So that most of the operating system decide, okay, instead of each step, I actually sacrifice some of the performance to prevent the deadlock. Let's just assume that deadlock never gonna happen. So I does not provide any solution for the deadlock. But deadlock do happens. Now what about this? If deadlock does happen, well, an easy solution is you turn off the computer system, okay? Or you randomly kill some of the processes. You just basically um, eliminate some of the process. So you manually break the deadlock. So the rest of the process is going to continue. Or if the deadlock happens, and the more deadlock happens, the performance suffers, and then you just actually reboot the machine. Okay, this is another solution. So that's a reality. So that's why I don't want to spend too much time on deadlock. Okay, but I just introducing the concept of a deadlock with an example. Okay, so that's pretty much all we want to talk about. And the next topic I would like to cover is the memory management. So now, before we discuss the operating system memory management part, let's first actually talk about the computer memory. Okay. Now, the computer physical memory, or sometimes we call it RAM, random access memory. Okay, it's a random access memory. Um, why it's called a random access memory? Because most of the uh, storage memory we talk about are not random access. So sometimes they are sequential access. For example, if you use the tape to store the data, like store your music, like using the tape. I I don't know whether you still remember the old day when people used the Walkman, like Sony Walkman. So they, use the music tape use the music tape. So the tape is not a random access storage. So in order to actually, if you want to hear a music, if you have a couple of sounds, some of the sounds are recorded at the beginning of the tape, and some of the music are recorded in the middle of the tape. So if you want to actually listen to the first music, you have to actually, start from the beginning. And if you want to actually listen to sound number 10, which is actually close to the end of the tape, then you have to actually fast forward the tape and to the location, then you can start to play the music. So that's not random access, that's sequential access. But memory is random access, which is good. Because if the memory is not random access, it's a sequential access, then when you store in a computer program, and then your performance may not be the same. It depends on where your program is stored in your memory. If you happen to store at the beginning of your memory, and then your program is running very fast. But if you happen to store the program in the back of your memory, suppose your memory is sequential, running from the start to the end. So then you have to actually, wait a long time until the computer actually CPU reach the end of the memory location, and then they can fetch the data from the memory. So now the performance of the program is depend on where the program is located in the memory. That's not good, right? So the random access basically means it will take approximately the same amount of time for the CPU to fetch the data in the memory. It doesn't matter which memory location your data is located. It will take us the same amount of time, approximately the same amount of time. So that's why computer memory is random access memory, which is very important. Okay, now the memory is organized into certain kind of pattern. So the physical memory, each memory can store a binary digital, like they can store a digital 0. They can store a digital 1. They can store digital 0. They can store digital 1. Okay. So it's a binary. So then when they organize the memory, they group the they actually configure the memory into a fixed size unit. Okay. So this each fixed size unit, it's called a cell or memory unit. Okay. Or sometimes we call the data a word. A word, So typically in modern computer system, the word size is 4 bytes. So it's a 4 bytes. 4 byte. 4 byte. So they just logically organized into certain kind of like a certain kind of actual format, 4 byte, 4 byte. And then each word has a logical location. So this is actually the locations number 0, 1, 2, 3, 4, 5. Depend on how big the memory going to be. It could be 2 million. Okay, the last one is 2 million. Okay, so that's okay. Honestly, 2 million is not the right number because normally the physical the number of words is typically the power of 2. So it's not 2 million. I can say what can I say? So it should not be 2 million. I can say like a 2 to the, okay, 10,000. Okay. So now this number also refers to as the memory address. So the memory address is basically a number that represent the location of a word. Okay. So a physical address is an integer in the range of from 0 to n minus 1. So suppose the memory has, let's say, instead of using the actual number, I can just use the the, 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 the character n. Okay. I can use the character n. Last one is n minus 1. Okay, so that's the last one. So the size, the memory contains n words. If each word is 4 bytes, you can say it's 4 n bytes, right? Because each word contains 4 bytes, and you have a total of n words. Okay. So the address consists of a fixed number of bits because the memory address it's actually organized as a 1, 2, 3, 4 n minus 1, but this number is also represented using the binary numbers. Okay, so the computer actually use certain bits to represent address. Now suppose the address we use k bits. Okay, so this is the k bits. Now, for example, it could be like the memory address used actually k equals 32. Okay, so which is actually most of the PC, we actually traditionally use the memory address k equals 32. So that means it's a 32-bit address. Now, modern computer may use actually 64 bits. Okay, because if we use 32 bits, how many different numbers you can represent with 32 bits?
2 to the 32.
No. So with 32 bits, you can represent a number in terms of binary as 0, 0, 0, and a total of 32 zeros. And then you have a 0, 0, 0, 0, 0, 1, that's 1, and 0, 0, 0, 1, 0. So you can actually start from all 0 all the way to 32 ones. And that's a total of 2 to the 32 different numbers. Okay. Now, what does that mean? So that means if I use k equals 32 bits to represent the memory address, so with this 32 bits memory address, I can represent, so the memory size, the maximum size for the memory is 2 to the 32 words, right? 2 to the 32 words. Okay. Now, if I use 4 bytes for each word, so the total memory size, the maximum memory size I can represent is 2 times 2 to the 32 times 4 bytes. How big is this? We can quickly figure it out. Okay. So so typically, so 2 to the 10 is 1024. Okay. So when we talk about 2 to the 10 bytes, that means it's a 1024 bytes. That's 1 kilobyte, right? Now, so every 1024 kilobytes is 1 megabyte. So that means 2 to the 20, which is 1024 times 1024 bytes. That's 1 megabyte. Now 2 to the 30 bytes is 1 gigabyte. Okay, 2 to the 30 is 1 gigabyte. Now, what about the 2 to the 32? 2 to the 32 plus times 4. 4 is actually 2 square, right? So 2 to the 32 times 2 square. So 2 to the 32 times 2 square, that's 2 to the 34. So now let's say 2 to the 34 equals 2 to the 4th times 2 to the 30. So that means it's 16, 2 to the 4th, that's 16, right? So it's a 16, 2 to the 30, that's 1 gigabyte, 16 gigabyte. Okay. Does it make sense? So that means if I use 32 bits, okay, and the 32 bits memory space, and then the maximal actual memory address I can use is, the maximal memory size is actually 16 gigabyte, which is pretty big, right? With modern PC now, I think a 16 gigabyte is not really, it's big, but not really that big, right? So when we, if you actually install your own PC, you probably if you try to actually buy a PC, a desktop, you're probably talking about in the neighborhood of 32 gigabytes, right? So that means 32 bits is not big enough for modern PC. It's okay, but it's not really that big. So then people start to talk about 64 bits memory address. That's really, really big. Okay. So now, so that's the the physical memory we're talking about. Now, to manage the physical memory, so we need to talk about another type of memory. It's called a logical memory. Okay. Why we need to talk about physical memory versus logical memory? Now, here's the reason. So, physical memory is here. Okay. So you have memory address from 0 all the way to n minus 1. Okay. That's a physical memory space. And the memory size you may use like n equals 2 to the k. So that means you use k bits. Okay. So use k bits to represent a memory address. Now, when you write a computer program, because eventually the memory going to be used to process the computer program, process the data, right? Now, when you write the computer program, so your computer program going to be, you write the computer program, and so your program is here. the program requires them eventually going to be loaded into the memory. So you have to make sure the program is organized in some kind of same format as the memory structure, right? So that means the program consists of a whole bunch of instruction. So you may actually load one instruction into one memory location, or in certain case, the instruction size is big, so you need 2 words, memory words, to accommodate one instruction. Now, depend on your CPU design, your instruction, depend on your instruction. Okay, because if you use an Intel CPU, versus the AMD CPU versus Motorola CPU, they may actually define completely different sets of instructions. Some of the CPU use more instructions, but each instruction takes very long memory space. So they may take 2 words for one instruction, and some of the instructions are short. They may take 1 word, but it's anyway. So the computer program is going to be actually consists of a whole bunch of instruction. Okay, so when you actually write the program, you compile the program, you create executable, right? Executable. Now, executable is actually the list of instructions. Now, these instructions has to be organized in terms like a memory. So then we actually call this a logical memory. So for each program, before the program is loaded into the memory, so we also going to say, oh, this instruction is in the location 0, 1, 2, and m minus 1. Okay. Oh, m minus 1 is already used, but I just say k minus 1, whatever. Or k is also used. So let's use another notation. I call it. Oh, let's say L. Okay. So that's the size of your program. So your program, so let's say each instruction going to be loaded into one memory location. Okay. So then from 0 to L minus 1, that's total of L instruction, right? The first instruction is 0. Second instruction is 1. So then when you actually load this program into the memory, instruction number 0 could be loaded into here, right? In the physical memory 500. That's 500 is the memory address. So the instruction number 0 loaded into memory 500 address, and instruction number 1 may load it into 501, right? So the whole thing going to be loaded here. Okay. Now this is called a logical address, and this is called a physical address. Now logical address always starts from zero because when you write your computer program initially, and before you load the program into the physical memory, and then you're going to always organize your program as the first instruction which has a logical address 0. Second instruction has a logical address 0. And you have another program, okay, which consists of a whole bunch of instruction, and that's also instruction address, instruction number 0. So the logical address for this one is also 0, and logical address 1, logical address 2, and here HIGL Q, okay, Q minus 1. Okay, so that's another program, and the memory actual instruction, first instruction versus second instruction, third instruction, and the last instruction is Q minus 1. Okay. So when you look at these 2 logical addresses, so it doesn't matter because This one has a logical address 0. This one has a logical address 0 because they are completely two different programs. However, when you load your program into the computer memory, you are not necessarily load the instruction number 0, which is logical address 0, into the physical address 0, right? You are not necessarily do this. Okay, so you don't actually necessarily load this. Now, even if you do this, say, I load this program into the physical address from 0 to L minus 1. I can do that, right? Okay, suppose you can do that. But for this program, the second program, so when you load it into the physical memory, so you cannot load this in logical address 0 to the physical address 0 because physical address 0 is already used. So the address should be unique, right? So you have to load this logical address 0 for this program into some other place. Okay, so there's a difference between logical address and physical address. Okay, physical address space and logical address space. Now, physical address space, there's only one address 0, but the logical, for different logical for different program, you may actually in a different logical address space, and each has its own logic address 0. But when you actually load each of the program into the physical memory, definitely you're not going to be able to load all these logical address 0 into physical address 0 because there's only one physical address 0, right? Why? If we want to support multiple programs, then you have to, figure out a way. You have to create some kind of mechanism so you can actually manage all these different programs in the physical memory. Okay. So that's why even though the logical address is an integer that ranges from 0 to n minus 1, that identifies a word in the logic address space. Okay. So before you try to execute the program, or before you load the logical the program into the physical address, then a logical address space is mapped to portion of the physical memory, and the program is copied into the corresponding location. Okay. So before you run the program, you have to load the program into the physical memory space. And then when you load, you are not necessarily load the physical logical memory address 0 to physical address 0. And I'm pretty sure that's impossible. Okay. It was the case though in the past, in 1980s, when the first PC was created. That PC only supported one program. Okay. So they used the DOS system. I hope you I don't know whether you understand or remember that old computer PC. And so if you actually check your basement, you may find the PC and your grandpa was using. Probably that PC is actually still there. They use DOS operating system. It's not even like a Windows. So then when you actually use the PC, that PC only can run one program at a time. Okay, not multiple programs like the piece the computers we are supporting now. So you can run multiple programs. So you have to use a scheduler to schedule all the programs when they share the CPU, right? But in the old PC, they only have one CPU, and each time only allowed to execute one program. So you have to load one program. Now, in that case, it's technically possible to load the logical address 0 to physical address 0. So you can exactly match the logical address and the physical address, which is really possible. but not anymore. Once you support the multiple, processes in the computer system, so each program, multiple program, going to be loaded into the computer actual memory. There's no way you can load each of the logical address 0 to the physical address 0, because if you have 10 programs and each program has its own logical address 0, so you have a total of 10 different logic address 0. So all wants to actually load into the physical memory address 0. That's really not possible, right? So that's why we need to actually figure out a way to do this. So to load the program into the physical memory, and then you need to understand the process of program transformation. Okay, when you write your program using Java, C, Python, and these programs are called source module, and we also known as source code. Source module is a program or program components written in symbolic language, okay, or we call it high-level language, okay, or you can use assembly language, which is also a symbolic language, okay. Now, it doesn't matter which one you use, like a high-level language or assembly language. Now, these languages cannot be directly loaded into computer memory because these languages are written in, which is close to like English language. So you need to translate this language into the language that the computer can understand, and the memory can be used to load this language. So then you need a compiler. For the high-level language, you need a compiler. For assembly language, you need something called assembler to translate these language into something called executable machine code. Now, the machine code is actually the instructions. The machine code is a whole bunch of instructions. Okay, so one instruction and after another. And if you use the pseudocode for the instruction, you may see some kind of code like a load something into the register from memory address like a 08 or something like this. LD, load, means load. So you may see some kind of a new what is called some kind of very actually simple word to represent some kind of that's actually, it's not a machine code. Machine code is actually all digit, binary digital, but this is more like assembly language. Okay. So once you compile the source code or assembly language into the machine executable code, then the first one you're gonna compile to is called object mode module. So it's a machine language output of the compiler or assembly generated from source module. The object module, you may actually execute the object module to perform the operation. Or sometimes the object module is not executable. So because the object module requires to run some of the functions in the library, so you need to link the object module to the library function. So basically, so the object modules may be linked together into a load module. The load module is the module that has the format of the memory setting. So the load module, the program in the load module is just, you can think about this as like a logical format. Okay, so load module. So the load module is a program or combination of program in the form ready to be loaded into the main memory and executed. So the load module can be organized into the structure that you can actually load into the memory. So it has the same structure as the memory structure. Okay, so that's why so you have to actually do certain kind of transformations from one format to the others. Now this is actually the diagram, which basically shows here's a source module. After compiling the code, you create a whole bunch of object module. And the object module, after you link all these object module together, you create a load module, and the load module can be loaded into the memory. Okay, so the load module basically consists of a whole bunch of instructions, and you can load it into the computer memory. Any questions? Now, since the physical address of the program components are not known until load time, okay, so the compiler and the assembler and the link assume the logical address space starting with the address 0. So let's say this is your load module, okay? So now you have organized into a whole bunch of instructions, and then you have instruction number 0, 1, 2, 3, 4. Okay. Now, here's the physical memory. 0 has exactly the same structure. So this load module actually has an instruction, and the instruction is actually organized into some kind of words. Okay. And here's the word. So you have exactly the same structure. So here's n minus 1, the last one. Now this program, now before you load the program, it's a logical. They use the logical address. So the address starts from 0 all the way to whatever the size of the program. It could be L minus 1, right? So this is total of L, the size of L words. So before you load it, you never know where you're going to load the first words, 0. 0 could be loaded into here, 100 or 1000. And then the second one, the instruction in the second word, going to be loaded into 1001, right? So the whole thing going to be loaded over here. Now suppose I load the whole program in the same consecutive area in the memory. The reality is that's not even true, because the logical, actually the program with the logical memory address may load into different part of the physical memory, not necessarily in this as a whole in the consecutive area. Why? Because you never know which part of the physical memory is free and which part of physical memory is not free, which is currently loaded by another program. Okay, so when you actually, before you load, so when you execute any computer program, if you execute it today, it could be loaded into the memory address 1000. Now, if I actually finished the program, and I actually, after a couple of hours, I try to run this program again. And so I load the same program into the memory. And this time, I may not load it into the same location. It could be, the program could be loaded into the memory location, not 1000 again. It could be loaded into 1500. Okay. So each time, you never know where you're going to load the program into the physical memory location. So that's why the physical address of the program components are not known until load time. So once you load the program in the physical memory location, then most of the time you know exactly which instruction, which was in the logical address is the first instruction, but in the physical memory address it may not located in the 0. Okay, so that's the thing. So that's why during the loading we're gonna relocate the physical logical address into the physical address, and then we actually, you know, do the address binding. We're gonna bind the logical address to the physical address. Okay. Now, during the physical the loading, the relocation, the program gonna relocate it to a different part of the, you know, memory address. Now there are a couple of different type of relocation. One is called a statical relocation. The other one is called a dynamic relocation. Statical relocation binds all the logical address to the physical address prior to execution. So that means during the compiler time, when you compile the code and you create the physical logical actually memory location, and then you can, you know, so you, before you start to execute the program, you completely load the whole program into the memory. So then every actually logical address basically maps to the physical address. It's done. Now, dynamic relocation is kind of different. Sometimes some piece of the code, when they load into the physical address, they still don't know where it is. Sometimes you only load a portion of this. Okay, so that's something we're going to talk about next time. Okay, so this is actually, so before you, the bottom line is that before you actually try to execute any computer program, which is organized as a logical address, you know, in the logical address space, you have to load the program into the physical memory address before you can execute it, because the CPU only fetch the instruction from the physical memory, not from logical memory, right? There's no logical memory, is just imaginary one. Okay, any questions before we call it a day? Okay, I gotta stop